Okay. Okay. So much better. So you can still hear me, right? Okay. Good. So why do we need lattice QCD? Since we know everything about QCD. The reason that we need lattice QCD is because we want to be able to calculate the properties of the theory at low energies, where objects that have to do with hadron structure are defined. And at low energies, the QCD coupling constant becomes strong. So the methods that you have learned that rely on perturbation theory are not going to be useful in this regime. So we need a non-perturbative definition of QCD. So how do we, in order to do that, the only actually known way of fully defining the theory non-perturbatively is through a lattice, through the lattice discretization. So you introduce a space-time lattice, and now the path integral that defines QCD becomes a bunch of a regular high-dimensional integral. And in fact, the continuum QCD that you learned about is defined as the limit of the lattice spacing going to 0. Much like the way you define an integral as the limit of a sequence of discrete sums, continuum QCD is possible to be defined as the limit of a sequence of computations done on a lattice where the path integral is nothing but a high-dimensional regular integral. So lattice QCD, apart from its practical reason of existence, which is to be able to do numerical non-perturbative calculations, one can view it as a formal definition of what QCD is. Now, in order to proceed with the definition of the theory, let me first remind you that in regular continuum QCD, you learn how to compute, let me get a better pen. You learn how to compute vacuum expectation values of time order products of various operators that live on space-time points. These are basically scattering amplitudes that can be written in terms of a path integral, 1 over z, which is a normalization, and then some functional measure of integration over the gauge fields and the fermion fields. And then you have the string of operators that whose vacuum expectation value you want to compute, and everything is weighted by the action of QCD. So that is a formal definition of any correlator of various operators that you need in order to describe a scattering amplitude that you want to compute. So in order to be able to do numerical computations, the first thing that we do is first perform the so-called wick rotation. So wick rotation is basically changing the physical time, which x naught, to go to an imaginary Euclidean time, as it's called. And with this transformation, our metric, which used to be G mu nu, which has plus and minus ones, it gets rotated to a Euclidean matrix, a metric which is delta mu nu. Now, the Euclidean QCD action is the same like the Minkowski space, I will drop the index xe here. Let's write it once. The Euclidean space-time is nothing but a sum over all the flavors that you have in the theory. And then you have gamma mu, but now Euclidean. There is the covariant derivative, but now I specify it as Euclidean. And the fermion mass and my fermion field, and then 1 over 4 f nu nu, f nu nu. And notice that I have all the indices written as lower indices because now there is no distinction between upper and lower indices. The sums are straight sums without any additional factors. And if you want, I can write you the mapping of Euclidean gamma matrices. The Euclidean gamma 4 is the same in some convention as the Minkowski gamma 0, and the Euclidean gamma k can be written as I times the Minkowski gamma k. And this immediately makes the gamma matrices now that used to be the anti-Hermitian, now they become Hermitian. The spatial gamma matrices, they become Hermitian in Euclidean space. And then one can write the chord algebra, which is now defines the gamma matrices, which is instead of having a delta mu nu, a g mu nu on the right hand side, you have a delta mu nu. So that's Euclidean space for you. And in order to proceed, we will have to introduce the lattice. We need to introduce a lattice, and in order to write down this theory, this integral over the action is a sum. So this make a schematic picture of what I'm talking about. You have a space-time lattice now. Everything is defined on this grid. I can write formal expressions. And so the fermions are going to be living on the sides of this lattice. And we will have to do something about the gauge fields, which we're going to talk about later. And this lattice, in order to be able to do numerical simulations, it will have to have some kind of boundary. But it's a finite box because I have a finite computer and I have to put everything in memory. So it has to be a finite box. Now the size of this box, L, is going to be, has to be sufficiently big. So it has to be much larger than hadronic length scales. And, but I have to do something about the boundary conditions. So in order to preserve some sort of translation invariance, in this case, when you have a lattice, you're going to only have translation invariance over discrete displacements, which are the lattice spacing, which I'm going to call it A here. In order to preserve some kind of translation invariance, you need to introduce periodic boundary conditions or anti-periodic boundary conditions. They both work. Now, for bosonic fields, we introduce periodic boundary conditions. However, for fermionic fields, one has to use anti-periodic boundary conditions. And this is related to the spin statistics theorem and the fact that fermions are Grassmann variables, which are anti-commuting. So in order to have the interpretation of the path integral as a time-ordered product of various operators, you need to introduce anti-periodic boundary conditions for the fermions. Yes?
Precisely is anti-periodic boundary condition.
So I can write you what is periodic and what is anti-periodic. So if I look at the fermion field on a space-time lattice, if I go along the spatial direction and I go, I shift by a step which is equal to the size of the lattice. So this is the periodic boundary conditions that the fermions satisfy in the, fermions satisfy periodic boundary conditions in space. Oops, that's not the right thing. In space is periodic boundary. I am not. So you have periodic boundary conditions, and when you have anti-periodic boundary conditions, which is in time, I will write it as LT hat to signify the shift in time, then you pick up a minus sign. So this is the anti-periodic boundary conditions. So in practice, since we started talking about boundary conditions, one can do crazy things, and you can have general boundary conditions that have the property that as you go around, you get some arbitrary phase, psi x. So this is sometimes they are called twisted boundary conditions. And these twisted boundary conditions have a practical use in the case of hadron structure calculations. I'm getting now on a tangent. I'm sorry about this. If you have periodic boundary conditions, you have done any simple calculation with, let's say, quantum mechanics particle in a box, you realize that the momentum is quantized. It gets certain integer increments or proportional to integer increments. Now, if you introduce this twisted boundary condition with the angle theta, then the minimum momentum, the momentum spectrum is shifted by theta. So by making theta small, you can achieve a lattice momentum that is less than 2 pi over L. And this has a practical application when you try to compute the nucleon form factor at very low q square, which is relevant for understanding, extracting the radius of the proton, for example. I don't know, here at Jefferson Lab, there were experiments trying to measure the nucleon form factor at extremely small q square in order to determine the radius of the proton, the charge radius of the proton. If you want to do that in Lattice QCD, in typical boxes that we use, the minimum momentum you can access is huge for these standards. Now, if you wanted really to probe small momenta, you would use this trick with these twisted boundary conditions. So that's a simple tangent. Now, the fermions are easy. We have the lattice, we put them on the sides. We know their boundary conditions. Now, the gauge fields, they are always going to have periodic boundary conditions because they are bosonic fields. So in order to deal with the gauge fields, we have to recognize the importance of the gauge symmetry in QCD. The gauge symmetry gives a very important property for QCD, makes the gluons massless. So in order, if we are to write down a lattice discretization of QCD that does not respect gauge invariance, then our gluons are going to be massive. And the mass of the gluon would be a lattice artifact. However, at finite lattice spacing, the theory won't behave the way we want it to behave. That's one issue that we need to deal with when we write down the lattice formulation of the gauge field. So the other issue that we would like to deal with is the fact that gauge invariance makes the partition function of QCD, the path integral, ill-defined because you have a symmetry. You can change your fields arbitrarily with the gauge transformation, and the weight factor in the integral is the same. So therefore, you have an infinity. by integrating across gauge equivalent field configurations. So in continuum QCD, you deal with that with a so-called gauge fixing procedure. And you probably know about the Fadeev-Popov procedure for fixing the gauge. You will go on and you perform calculations in this gauge fixed world. However, when you compute physical observables where you have, they are gauge invariant by construction, this gauge dependence drops out. And that's a good check of analytic calculations to make sure that they don't depend on the gauge. Now, on the lattice, we have the advantage that we can actually, in one shot, solve both problems, preserve gauge invariance and avoid having to do this gauge fixing procedure. And this is done by a trick that Ken Wilson in '74 came up with to introduce gauge fields not as fields that live on sites on the lattice, but as gauge links. This is if I'm sitting at the point X, and this is my direction mu hat, I have a gauge link X of X, u mu of X, which can be written as, it is written as the following, is the path ordered exponential e to the I from point X to point X plus mu dx mu, or dy mu, let's say, a mu of y. And then I have to have this coupling constant as well, g, in front of it. So this path ordered exponential of the gauge fields, the continuum gauge field that is supposedly living on the site or on the path that this gauge link is defined. So these gauge links are members of the SU3, in the case of QCD, SU3 Lie group. And they are compact variables. They are unitary matrices because the gauge fields are, as we know for QCD, they belong in the algebra of SU3 and they are traceless anti-Hermitian matrices. So these gauge links are unitary matrices. The unitary matrices live on a manifold that is compact. SU3 gauge group has a compact manifold. So instead of integrating over the gauge fields as we do in the continuum, on the lattice, I'm going to integrate over gauge links that live on the SU3. Yes?
Could you please explain what does it mean to field to be the manifold to be compact?
Huh?
Does it
compact? It has a finite volume. So for example, if you look at the SU2, which is a simpler manifold, so the SU2 is a three-sphere. It's you can think of it as a sphere embedded in 4 dimensions. It's a three-sphere. It's a surface, a three-dimensional surface, which is a sphere. So the volume of that manifold is finite. So if I integrate, if I do this integral d u mu on a one gauge link, it's going to be some volume of SU3, which is a number. It's not infinite. So if I did the integral of dA mu on its own, it's going to be infinite. Now, if you have the continuum action and you try to do this integral, you might say, oh, I have this action that it dumps the fields at infinity, so this might be finite. However, you have a flat direction, which is the gauge symmetry direction. So as you integrate over this flat direction, you get infinity. If you want, one can think of a simple two-dimensional function which has a, let's say, parabolic e to the x squared in one direction, but it's flat in the other direction. there is no dependence in the other direction. If you integrate dx, dy e to the minus x squared, this is infinite because the y direction has no damping. And this is the same story happens in the case of the gauge fields. You have these directions in the field space that are that the action doesn't depend on. These are the gauge equivalent directions. So if you try to integrate over the continuum gauge fields, you will get infinity. So if you did the same thing with the lattice formulation where you have the gauge links, which are SU3 variables on a finite volume, yes, there are directions where the action doesn't depend on those, but you integrate over them, you will get a number. It's a finite space. Okay. So that's the main idea. And oops, I'm skipping stuff. That's the 7, so 8 here. Okay. So now, what are the gauge transformations in continuum on the lattice? So in the continuum, you know that you have a gauge transformation of the gauge field, which is a rotation by a unitary matrix omega, and plus the gradient of that matrix. Now, if you perform the gauge transformation on the underlying gauge field, then you would, and you ask the question, what happens to this gauge link? You realize that the gauge transformation on the lattice becomes this omega dagger of x plus mu. And so now let me get my bearing again. This is here, 6, 7, 8. Okay, so now you might ask the question now, how do I write down the gauge action in terms of these variables? I know that the gauge action is written in terms of F nu, which is related to the underlying gauge fields. So what is the gauge action when you work on the lattice? So in order to do that, let's first ask the question, what does the gauge action going to be like? What is the main property of the gauge action? The main property of the gauge action is that it is gauge invariant. So, and the simplest consideration to have in order to figure out what the gauge action would be is what are the gauge invariant objects you can write down in terms of these gauge links. Now, with this gauge transformation property, if I look at one plaquette, if I look at one unit cell of the lattice, and then I look at how this gets transformed, you get an omega of x on this point. If this is point x, you get an omega dagger of x plus mu here. And then if you now look at the link that goes around here, this will be transformed by the omega on one side, omega dagger from one side, not going to be the omega. Let's write it again, omega of x plus mu, and it would be the omega of x plus mu dagger up here. So this is the transformation that happens in this point. And now you can see that if I multiply together this guy with that guy, if I multiply together u mu of x times u mu of x plus mu, u nu of x plus nu, which because this is the mu direction and this is the nu direction. If I multiply the two together and ask the question, what happens under gauge transformation, you will see that the two links, the two gauge transformation matrices that are inside are going to cancel. And it's not very hard to realize that if I now go and multiply this link and that link together to close a loop, all the gauge transformation matrices that appear on these corners are going to appear both as they are Dagger and they are non-Dagger, and they will be multiplied together. So this closed loop is going to be gauge invariant, which is the product of the gauge links around u mu, and I have to take the trace of the plaquette because the last two things have to cancel, which is the trace of u mu of x, u nu of x plus mu, u mu Dagger, because I traversed the lattice in the wrong direction now, of x plus nu, and then u Dagger of nu of x. So this is my closed Wilson loop, which is this is gauge invariant. Gauge invariant. Okay. So this is the fundamental gauge invariant object that you can write. It's the smallest closed loop traced on the lattice gives you a gauge invariant quantity. So therefore, this could be a candidate for the gauge action. And let me write down the gauge action in the on the lattice. I will write it as beta times sum, and I will explain what beta is, over x, and sum over all mu and nu. And I do 1 minus 1 over NC, where NC is the number of colors. It's 3 for QCD. And I take the real part of the trace of the P mu nu that I wrote in the previous slide. So this is the gauge action. Action of QCD, of lattice QCD. Now, beta is a proxy for our coupling constant, which is 2nc over g squared, and g squared is the coupling constant that we have in the continuum QCD, which in the case of SU3, it is 6 over g squared for SU3, because NC equals 3, number of colors. Now, why is this the gauge action? In this case, I will give you a homework. I would ask you to compute a homework. So how do I prove this, that this indeed is the gauge action? So what I really want to prove is that that this gauge action that I wrote down, if I take the limit of the lattice spacing going to 0, becomes 1/2 integral d for x trace of f mu nu. So if you want to prove that, you will, let's see, I'm getting confused here with my notes. Where am I? Okay, so in order to prove that, you will have to start from the following. So if you, as you know, the gauge link is an exponential of a matrix. And you will have to multiply exponentials of matrices. So you will have to do a computation like the one that I'm writing here. So it turns out that because the matrices are not computing, this is 1/2 times the commutator of the two matrices plus more terms. Now, a key thing is that if you remember, the gauge, the definition is an integral. So If I go and write down my lattice action, my lattice version of the gauge link, it's not an integral. It's E, G, the lattice spacing times the gauge field. This is basically trapezoid rule for calculating an integral with a single point. Okay, it's the length times the value of the field on the point. So these are the things that you have to compute. So these matrices that you are going to exponentiate come with the lattice spacing. So the commutator is going to be 2 powers of the lattice spacing, and the terms that are I'm not writing here are multiple commutators. And they are going to be higher orders in the lattice spacing. So you are interested only in the leading expression, in the leading contribution in terms of the lattice spacing. So you are going to drop the higher order terms. So you are going to keep the commutator. Now, on the lattice, the gauge field at some point x plus some lattice spacing, you can expand it in Taylor series and have it written as A times the derivative of, depending on what direction am I here, let's say nu hat, times the derivative in the new direction of A mu of x, plus higher order terms. So your gauge fields that would appear on different points can always all be expanded in Taylor series and brought back to the origin of the plaquette. So with these two tricks, two realizations, it's straightforward algebra to go and do this. So if you perform the calculation, then you will find that the plaquette, the p mu nu of x, is nothing but the exponential I g a squared f mu nu of x plus order a cubed. So that's what you find. And so if you expand in terms of the lattice spacing, then you get 1 over a 1 f mu nu of x. And if I kept my additional terms that are order a cubed or higher, in fact, order a cubed doesn't contribute, you get g squared a to the 4th over 2 f mu nu squared plus higher order terms. So now you can immediately see that if I take the trace of p mu nu, if I take the trace of p mu nu of x, because f mu nu, what is f mu nu? Is the generators times some weights, right? Where tau are the generators of SU3. So if you take the trace, the first term cancels. So you only get g a to the 4th over 2 trace of f mu nu squared. And this is precisely the term that you need in order to write down the action. So I urge you to want to understand how this works, to go do the algebra that I pointed out. So this is one component in this algebra, and this is the other component, and you can organize the calculation and do it. So now we are done with the gauge fields. So we need to discuss what's happening with the fermion fields. Oops, time is flying. So again, the action of the fermion field, I can write it as in the continuum, as you know, with Euclidean is psi bar, gamma mu, d mu, covariant derivative, m fermion, or whatever it's the fermion, psi, is the action. And now the covariant derivative, d mu, in the continuum is partial mu plus I a mu of x. But now how am I going to write down a derivative on the lattice? If I want to calculate just a simple derivative of a fermion on the lattice, you will have psi of x plus a mu hat minus psi x minus a mu hat divided by twice the lattice spacing. So to first order plus order a squared. To first order in the lattice spacing, the simple derivative is given by this finite difference. Now, if I want to write a covariant derivative, what is the purpose of a covariant derivative? The purpose of the covariant derivative is to have a derivative that is sort of gauge covariant. So if I take the covariant derivative and I try to discretize on the lattice, I will get a very similar expression as the naive derivative. However, what I have to do here is I have to make sure that I transport the fermions with the appropriate gauge links so that I retain gauge covariance. Psi of x plus mu, one lattice spacing minus u, and now it is a little bit tricky because the links x minus a mu hat psi of x, and I will write here minus mu a hat. And that is my covariant derivative. And it is by construction is covariant because the fermions under gauge transformation, they transform like in the continuum. You multiply by psi of x, and the gauge link has the omega. So if I go in this point here, come on, go here. If I go in this point here, this guy gets an omega of x plus mu, while the gauge link gets an omega dagger of x plus mu, and they cancel because these are unitary matrices, and you are left with this omega of x. So this d mu that I defined, this d mu psi, under the gauge transformation is covariant. It picks up an omega of x, d mu of psi of x. So this is my definition of the covariant derivative. If I was not scribbling that badly, it would have been. So is it visible? Shall I rewrite this and to make it cleaner? I will minus u mu dagger of x minus mu a psi of x minus mu at a, and I will erase this now that it's no longer needed. Okay, now let's so this is the covariant derivative. So if I wanted to write down my naive fermion action, I would, and I will call it naive, and you will see why I call it naive. It is a to the fourth from the integration x, and then I have my lattice covariant derivative, which I can write it psi mu, d mu. I will put the word lattice here so that I don't write too much, plus the mass psi of x. So that is my naive fermion action, where this d lat is given by the expression that I have up here. Now there is some obvious problems with this expression, and these problems appear when you go to the free field limit, where you set the gauge fields to 0 or the gauge links to 1, and you calculate the momentum space, the free quark inverse propagator in continuum language. So in the free field, the gauge fields drop out, and we deal with only the fermions. Now, if you use this finite difference discretization for the derivative and you work out things, and I will urge you to do that as a homework if you care to, you will find that in momentum space the propagator becomes like this, sine p mu times the lattice spacing. That's the fermion momentum plus the mass. So that is the form of the fermion propagator. Now, as I discussed before, these momenta on the lattice are going to be discrete versions of so because of the antiperiodic boundary conditions, I will write it in this form plus k mu, where k mu is, is 2 pi n over L. It's where n is an integer. Now, this funny notation that I have here is mu equals 0 if mu is 1, 2, 3, and eta mu is 1 if mu equals 4. So this is the antiperiodic boundary condition, adding this contribution to the fermion momentum. But now, if you make a simple plot of this d as a function, let's say, of the momentum, and I'm taking the imaginary part of d. Let's write it here, the imaginary part of d. And let's say one spin component. So you will see that this is a sine function that will go like this, and this is pi over a. Now, at low momentum, this dotted line is what the fermion propagator in the continuum is. So, and I'm going to write it here. The continuum is going to be A times P mu plus M. So if you expand the sign in when the lattice spacing is small and the momentum is small, the lattice spacing drops out, and you come up with the continuum fermion propagator, free field fermion propagator. And in fact, the continuum free field fermion propagator is this straight line if you wrote it in terms of momentum. So what does the lattice do for us? The lattice gives us a sign, and if you go to sufficiently large momentum, you deviate from the continuum. So you might think that this is not a big deal, but in reality, it is a big deal because the pole of the propagator is basically signifies the existence of a particle of a particular mass. If you take the momentum to 0, you have a mass, that's your particle. Now, in the case of the naive fermion discretized action, you see that you have a 0 here. So you have, if you take the inverse propagator, you will have a pole that appears at low momentum and the pole that appears at momentum pi over a. So if you wanted to ask the question, what are the light degrees of freedom that are described by this propagator? In one dimension, there would be a light degree of freedom that appears here, and this would be also a light degree of freedom that appears over there, although its momentum is very high. So that is the so-called fermion doubling problem. Fermion doubling. So what fermion doubling does for you, it takes, you start with, let's say, a single flavor of free fermion in the continuum theory, and you put it on the lattice, and all of a sudden you realize that you have two fermions, light fermions on the lattice. in fact, as you can see, if I go to d dimensions, this picture is going to be to appear in every single direction. So in d dimensions, you will have 2 to the d fermions. So in 4 dimensions, you're going to have 16 light fermions. And that is the famous fermion doubling problem, which we need to solve in order to be able to do calculations with the right number of flavors. In fact, how do we solve this problem? Before I tell you the solution, I will first tell you about a no-go theorem that came about in 1981, which says that it goes by the name of Nielsen-Ninomiya theorem. Let's say it's called Nielsen. How do I spell it? Ninomiya theorem. It's a no-go theorem, which means that you cannot do something. This came about in 1981, and it says that, I'm not going to be very formal about it. The key ingredient is that the massless fermion in a free field, in QCD, let's say, or in any fermionic theorem. So massless fermion has the so-called chiral symmetry. We know what the chiral symmetry is. So I can write an expression about, I see some people nodding. So chiral symmetry means that the Dirac matrix commutes with the gamma 5. So if you have chiral symmetry and you discretize this fermion action that in the continuum has chiral symmetry, and you demand that the discrete action is local, then you are always going to have fermion doublers. So Nielsen-Ninomiya is telling us that you cannot avoid fermion doublers, fermion doubling problem, if you want to preserve locality of your lattice action and chiral symmetry. And this theorem has stuck around for many years and actually has great implications about what do we do about lattice fermions. And in fact, if we ask the question, what happens to our naive fermion action? The naive fermion action has chiral symmetry because gamma 5 anti-commutes with the gamma mu, and therefore this anti-commutation relation is satisfied. So according to Nielsen-Ninomiya, I will have fermion doublers. And it's also local because it only has nearest neighbor interaction. So therefore, according to Nielsen-Ninomiya, we're not going to be able to avoid the fermion doubling problem. Now, what do we do about this? So in fact, from the very beginning of lattice QCD, Ken Wilson, who wrote down the theory on the lattice, solved the problem right away. So the Wilson fermion action goes as follows. I will write the expression and talk about it. It is psi bar of x, and then I have gamma mu. I will write it, let's see, with this operator as my derivative, because I want to preserve the symbol d as the Dirac operator. But then he adds a new term into the action, which is given by this delta mu, and then plus m psi of x. So the mu is covariant gradient. Let's write it this way, which we wrote it before. Delta mu is covariant, or sum over mu. Sum over mu goes here, and sum over mu goes here. So this is covariant Laplacian. So in other words, this is the second derivative. So what is the covariant Laplacian? I will write down the second derivative with respect to mu of some function psi of x. You write it as psi of x plus a mu plus psi of x minus a mu minus 2 psi of x divided by a squared. And if you do Taylor series expansion, you will see that the leading terms cancel and you get something that is, you get the second derivative plus higher order corrections. So how do I convert this into my covariant Laplacian? It's simple. You multiply by the gauge link on whenever you see a displaced field. And here you do dagger x minus mu, psi of x minus mu, minus 2 psi of x, divided by the lattice spacing squared. That is my second derivative in the covariant form. So, and so that writes down the Wilson axiom. Let me say one thing before I go forward, because I keep on writing this. So you see, I have this term psi of x minus a mu hat times u dagger of x minus a mu hat mu. So why do I have this? On the lattice, I look at a point x and I store the gauge link that goes forward. So when I am trying to compute the derivative or transport this field from the x minus mu point, I need to use that gauge link. But on the lattice, I have stored that gauge link, and that gauge link is mu of x minus a mu hat, because it's sitting here. And now we are time over. Okay. So let me give a quick summary before I finish. The first thing to note is, give me 5 minutes so that I don't leave it, that the Wilson action, if I go to the free field, I have dp equals I over a sum over mu gamma mu sine p mu of a plus r, which r is an arbitrary constant, usually set to 1, and it is the Wilson parameter, cosine p mu a, and then, so that is my propagator, and then if I have a mass plus m. So if I look at this expression now, you see that as I take p going to 0, I have a pole. So for the D inverse. But if I go p going to pi over a, the cosine becomes minus 1, and I get this d of pi over a goes to something that is proportional to 2 r over a. So plus the mass. So if I ask the question, what is the mass of this particle that used to be the doubler, it's going to be the mass that I had before plus this term. So if I take the continuum limit now, the mass of this particle is not going to go to 0, it's going to go to infinity because the lattice spacing goes to 0. And this is how the doublers are eliminated from the spectrum from the physical spectrum, which is the low energy, when you take the continuum limit. Their masses go to infinity. Now, the big problem of Wilson fermions is the fact that the second term that I have written here, which is the Wilson term, does not contain a gamma matrix. And therefore, it does not commute with, anti-commute with gamma 5. It's basically like a mass term. And it breaks chiral symmetry. So you have no doublers, but you have broken chiral symmetry. So that is the problem of Wilson fermions. And I'll stop here. Let me summarize. I gave you a quick introduction of the formulation of QCD on the lattice. We talked about how to write down gauge fields. We talked about how to write down fermion fields. We talked about the fermion doubling problem. We preserve gauge invariance on the lattice. And now we're ready to do computations. Okay, so I'll stop here.
Thank you very much. Any burning question? Only one or two max. Then we have to coffee break.
Yes.
When we were initially defining P mu, there was a point where you were taking n mu to be 0 or 1, depending on whether it's the spatial or the time direction. Could you talk about why the time direction is constructed that way?
It's because it's anti-periodic boundary conditions.
Oh, to ensure that, okay, I see.
Yeah, and that's why the
Want
quantization of
time
momentum
direction to be anti-periodic, actually. Like,
Huh?
I was also meaning to ask. why you
Yeah,
want that to
it's
be anti-periodic.
it's because if you want to have, okay, so have you thought about thermodynamics in QCD? So if you want to write down the partition function with a finite time extent, this finite time extent is giving you a temperature. So when you do thermodynamics, you have a finite time extent, and that the length of the time is the inverse temperature. So if you want it to, if you have Grassmann variables, which are the fermions, and you want to have this thermal interpretation of the path integral, you must have anti-periodic boundary conditions in time for fermions. So that's the 5-second answer. So that's the reason. Now, details are more complicated to explain. But now, if your goal in life, though, is not to do thermodynamics, but you want to do hadronic physics, which means that you want to have a very large box compared to the hadronic scales to calculate the properties, the spectrum or the structure of a hadron or anything. These boundary conditions are not going to matter because the box is going to be much, much bigger than the scale at which you are probing your system. So you can do lattice QCD with periodic boundary conditions in space, in time, or anti-periodic boundary conditions in time, and you won't see a difference. You can put Dirichlet boundary conditions, you can do whatever you want, you can do even twisted boundary conditions. If you are talking about hadronic physics, where the size, the physics you are probing is at a distance scale that is much smaller than the size of the box, the boundary conditions don't matter. But if you want to do thermodynamics, then it does matter. Okay.
One more question. Only one. Seems not the case. We can have coffee break.